So the two major issues with Bohr's model of the atom was that it could not explain two concepts. The first one is dual behavior of matter, and the second is Heisenberg's uncertainty principle. The Heisenberg's uncertainty principle, we'll talk about that in, I think, after the two videos. But now we are going to be talking about dual behavior of matter. So basically, Einstein was the one who suggested dual nature of light. If you remember, we discussed about that in one of the previous videos. So it behaves as both a particle as well as a wave. De Broglie was the French scientist in the year 1924. He said that like light, even matter has dual nature. So microscopic particles like protons, electrons, atoms and molecules, they behave both as a particle as well as a wave. So according to de Broglie, all material particles in motion possess wave-like characteristics. So wavelength, that is lambda, is given by the equation h by mv, where h is the Planck's constant, m is the mass, v is the velocity, and mv equals to p, that is the momentum. So according to this equation, lambda equals to h by mv, which is equal to h by p. So waves associated with material particles are matter waves or de Broglie waves. So let's see as to how he would have probably derived this particular equation. Now, first of all, according to the Planck's equation, we know that E is equal to h mu. Okay, and according to Einstein's equation, we know E equals to mc square. So h mu equals to mc square. Not only this, we know that mu equals to, or rather lambda into mu equals to c. So mu will be equal to c by lambda. So hc by lambda equals to mc square. This and this gets cancelled. Okay, and then when we rearrange this equation, we get h lambda equals to mc. So lambda will be equal to h by mc. Now c is nothing but the velocity. So v is velocity, c is also velocity of light or electromagnetic radiation. So this particular equation is also applicable to photons, and the equation is also called as the de Broglie's equation. So lambda equals to h by p, which is nothing but Planck's constant divided by the momentum. Okay, that is how he came up with this conclusion. Now, this Planck's constant has a definite value, right? Obviously, as its name suggests, it's a constant. So, lambda is inversely proportional to the momentum. Okay, so lambda is inversely proportional to the momentum. Okay, this is what we get from the equation over here. Now, this particular equation is applicable even for particles with large masses. Now, let's take two cases. Okay, one case we'll take a ball which is moving at a particular speed, and in another case we are going to be talking about an electron. Okay, so let's start. So, in case of an electron, in an electron, we know that the mass of an electron equals to 9.11 into 10 to the power minus 31 kilograms. Okay, and we need what? We have the mass, we need the velocity. So velocity of this electron is assumed to be 10 to the power 6 meters per second. So we have the mass, we have the value of velocity, we know the Planck's constant, so we can calculate the wavelength, and that is 6.63, we're rounding it off, 6.63 into 10 to the power minus 34 kilogram meter square, because joules, right? Joules to, which is converting it, divided by m, that is 9.11 into 10 to the power minus 31 kilograms into 10 to the power 6 meters per second. So the wavelength of this particle is 7.28 into 10 to the power minus 10 meters. Okay, now the wavelength is very, very small. Now let's calculate the same for a moving ball and then compare. Okay, moving ball. So the mass of the moving ball is assumed to be 10 grams and its velocity is assumed 10 to the power 6. We are assuming both these objects are moving at the same velocity. So 10 to the power 6 meters per second. Okay, now when you have to calculate lambda, 6.63 into 10 to the power minus 34 kilograms meter square second inverse divided by 10 into 10 to the power minus 3 kilograms into 10 to the power 6 meters per second. Okay, so when you simplify this, you get 6.63 into 10 to the power minus 38 meters. Now the wavelength of this and this is if you see, this has 10 to the power minus 10, which is relatively higher than 10 to the power minus 38. Also, this particular value is actually measurable. So we know that this particular value is almost similar to that of X-rays, and so the wave characteristic of the electron is observable. However, for a moving ball, this value is too huge, rather it is too small for us to observe the wavelength, and we don't have the equipment to actually measure the wave characteristic of a moving ball. And so that is why as the mass increases, the wavelength is too small. If you remember, we spoke about momentum as well, right? So, but here is specifically talking about the mass and the value of lambda. So as the mass increases, the wavelength will decrease. Okay, so that is why for bigger objects or macroscopic particles, it is not possible for us to figure out or observe the wave nature directly. Now for the dual nature of electrons, there were two things, they were scientifically proven using various experiments. First of all, the particle nature. So electrons, it has a particular mass, it has a definite charge, and it has a definite momentum. So they are a characteristic of a particle. Also, when an electron, if you remember, we had spoken about cathode ray tubes and the use of zinc sulfide where it showed fluorescence. So each electron would show only, it would basically interact with it and it lead to only one spot or scintillation. And so this meant that it had a particle characteristic. Wave nature, it was experimentally verified by Davidson and Germer in the year 1927 and George Thomson in the year 1928. Now, electrons, so the electrons show various properties that are similar to that of waves as well. They undergo diffraction. So diffraction basically happens when a beam of light is passed through a small narrow aperture and it spreads out. So because an electron acts as a wave, it shows the property of diffraction. And so this particular property of electrons acting as waves is used in various experiments. Specifically, it's used for the electron microscope. So an electron microscope observes the interaction of electron with an object, and it can achieve a magnification of about 15 billion times. So in the next video, we will be solving a few in-text questions with relation to dual behavior of matter.